We often hear that nothing can travel faster than light. According to Einstein's theory of relativity, this is true for any object carrying information or energy. But then you might come across surprising statements like, "A shadow can move faster than light." Wait, how is that possible? Wouldn't that break physics? Let's explore this step by step. Imagine you are standing next to a wall with a flashlight. You hold your hand close to the wall and move it side to side. You'll notice your shadow also moves, usually in the same direction and speed as your hand. Now, what happens if you move your hand farther away from the wall while still swinging it quickly? You will see that your shadow on the wall grows larger and it starts moving faster than your hand. In fact, if the wall is far enough away and you move your hand fast enough, the tip of the shadow can move across the wall faster than the speed of light. You might ask, does that mean the shadow is actually moving faster than light? The answer is no. A shadow is not a physical object. It does not carry mass, energy, or information. It is simply the absence of light. When you move your hand, different light rays are blocked in slightly different directions. The point where the shadow appears is just where the light has been blocked. No physical thing is traveling across the wall. Another example. Imagine shining a laser pointer at the moon and sweeping it quickly across its surface. If you could do this fast enough, which is extremely difficult, the spot of the laser might seem to move across the moon's surface faster than light. But again, no single photon is traveling sideways across the moon at superluminal speed. It is just the point where your beam happens to land at each moment. So, why does this not violate Einstein's theory of relativity? Because relativity only forbids objects, or signals, things that carry information, from traveling faster than light. A moving shadow or laser spot does not carry any real substance or signal from one point to another faster than light. You might also ask, can we use a fast-moving shadow to send a message faster than light? No. Since the shadow's motion depends on your local movement and does not involve any material traveling across the screen instantly, there is no way to use it to transmit actual information from point A to point B faster than light. In short, when we say faster than light shadows and geometric projections, we mean that some visual effects or projected points can appear to move faster than light, but this does not break the laws of physics. It's a beautiful example of how our intuition can be tricked by geometry and perspective, even though fundamental physics stays perfectly intact. These concepts also appear in astronomy. For example, when observing the shadows of objects in space, or the sweeping of light beams across clouds or nebulae, these projections can look like they move incredibly fast. But no physical part of the system is actually breaking the cosmic speed limit. Next time you play with shadows on a wall or see a sweeping laser beam, you can think about this hidden lesson in relativity and geometry. A reminder that physics can surprise us, even in the simplest, everyday experiences. A shadow is formed when an opaque object blocks light, creating a region of darkness on a surface behind it. Unlike a physical object, a shadow is not a material entity but rather a geometric projection of the object's silhouette. The shadow's shape and speed depend on the light source, the object's motion, and the projection surface. Because it is not a physical object carrying energy or information, a shadow can exhibit properties that seem counterintuitive, such as superluminal motion. Understanding shadows as projections helps separate them from objects constrained by physical laws like relativity. A small object moving slowly near a flashlight can cast a rapidly sweeping shadow across a distant wall. Like a moving finger creating a quickly sweeping laser pointer dot on a distant screen, the shadow's motion reflects projection, not real travel. When an object close to a light source moves, the corresponding shadow on a distant screen can appear to travel extremely fast. As the distance to the screen increases, small angular movements of the object map onto large lateral displacements of the shadow. If the screen is sufficiently far away, the shadow's edge can traverse it faster than the speed of light. However, this apparent speed is a geometric effect, not an actual transmission of matter or information. No part of the shadow physically moves from one point to another in space, carrying energy. A pencil rotated slowly near a lamp can make its tip shadow race across a far wall, seemingly instantaneously. Like the sweeping beam of a lighthouse, seeming to cross the horizon instantly, yet no material entity travels that quickly. Special relativity asserts that no information, matter, or energy can travel faster than light in a vacuum. A shadow does not involve the transfer of mass or a signal capable of conveying information faster than light. It is merely an absence of light that dynamically changes position, controlled by local object motion and light propagation. Even if the shadow edge moves at superluminal speed, causality is preserved because no event at one end can instantaneously influence events at the other end. Thus, the phenomenon is fully consistent with Einstein's relativity principles. Even if a shadow moves across the moon's surface faster than light, no message or energy is transmitted superluminally. Like a stadium wave appearing to travel fast around the arena, though each fan moves only locally and in sequence. The concept of light cones describes how information and causal influence propagate in spacetime. Each point affected by a shadow is only determined by the local light path from the source, modulated by the object's position. The apparent faster-than-light motion is a result of extrapolating these local light paths over large distances. The shadow front may appear to cross large areas quickly, but each segment is governed by separate, causally connected light trajectories. This reinforces that no violation of causality or space-time structure occurs. A distant screen's points turn dark sequentially, each moment determined by earlier light blockages, not by an instantaneous global change. Like dominoes falling in sequence along a line, each segment of the shadow is set by preceding local events. When projecting over great distances, small angular displacements of the object result in large linear displacements of the shadow. This geometric amplification is akin to how a tiny movement of a laser pointer close to the wall causes a large shift of the laser spot far away. The linear speed of the shadow edge scales with the distance from the light source and the object's angular speed. As this distance increases, the apparent velocity can exceed the speed of light, arbitrarily. Yet this is purely an optical illusion without physical substance. A cat walking in front of a street lamp can make its shadow sweep quickly across a distant building facade. Like a small steering adjustment causing a car to veer widely at high speed, small motions project into large, distant effects. Shadows should not be confused with physical wave fronts such as shock waves or electromagnetic pulses. Physical wave fronts involve the propagation of energy and can at most travel at the speed of light in vacuum. A shadow lacks intrinsic energy or momentum. It is simply the absence of photons reaching certain points. Therefore, even though it seems to move, it does not displace any medium or transmit energy. This fundamental distinction underlies why shadows are exempt from the relativistic speed limit. The shadow of a rotating fan blade on a wall is not a physical wave, but a moving region where light is blocked. Like the outline of a cloud drifting across the ground, the shape moves, but no matter or energy is being swept along. Since shadows do not carry information independently, they cannot be used for faster-than-light communication. Attempting to encode a message by moving an object to create superluminal shadow motions would fail, because each point on the screen can only respond to local light changes causally limited by light speed. The illusion of instantaneous motion does not translate into practical instantaneous signaling. As a result, such phenomena do not challenge or undermine relativistic causality constraints. Trying to send a Morse code message by rapidly moving a shadow edge would still be limited by the original light source propagation delay, like waving your arms to create a pattern in a field of wheat. The pattern moves, but the signal spreads only as fast as the local disturbances. Demonstrations of faster-than-light shadows are often used in physics education to illustrate the difference between geometric projections and physical objects. Simple experiments with projectors, walls, and small rotating objects can effectively reveal these effects. They help students understand light propagation, angular motion amplification, and the non-material nature of shadows. Such experiments can clarify common misconceptions about faster-than-light phenomena and reinforce principles of special relativity. They also highlight the power of geometric optics in explaining seemingly paradoxical effects. A classroom experiment with a laser pointer and a distant wall shows how slight wrist motions make the spot move rapidly across the wall. Like magic tricks that reveal optical illusions, these experiments show the difference between appearance and physical reality. The phenomenon of superluminal shadows invites deeper reflections on the nature of motion, information, and causality. It emphasizes that not all visually fast movements imply actual physical travel. Shadows, as intangible projections, remind us that many seemingly paradoxical effects arise from geometric or perceptual tricks, rather than fundamental physics violations. This distinction underscores the importance of careful reasoning when interpreting extreme or counterintuitive observations. Appreciating these nuances helps deepen our understanding of the boundaries set by the laws of physics and enriches scientific literacy. Observing a giant shadow sweeping across a mountain ridge inspires wonder, but also reveals the subtlety of light behavior. Like seeing reflections move across a lake faster than a boat could possibly travel, these illusions teach us about the limits of perception versus reality.